Every Mars mission plan ever drawn up has the same problem buried in the math. Getting there is hard. Getting back is nearly impossible. And the people who have spent their careers working on this have quietly arrived at a conclusion. The press releases don't say clearly that the first humans to reach Mars will almost certainly stay there. Not because something went wrong, not because of a malfunction, a disaster, or a failure of any kind, but because coming back is, by every honest calculation, the hardest part of going at all. This is why the most serious mission architects aren't asking how to bring the crew home, they're asking what it takes to keep them alive once they're there. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath, and let's begin. Mars has occupied the human imagination for longer than telescopes have existed. Ancient cultures watched that faint reddish light wander slowly across the sky and assigned it meaning: war, danger, the restlessness of something that would not stay still. They were not entirely wrong. Mars does not stay still. It circles the sun on its own elliptical path, sometimes swinging within roughly 55 million kilometers of Earth, sometimes retreating to more than 400 million kilometers away. For most of human history, it was nothing more than a point of light. Then the telescopes came, and the point of light became a disk, and the disk revealed features: dark patches, polar caps, a surface that changed with the seasons. The imagination did the rest. For a century and a half, writers and scientists and dreamers populated Mars with canals, civilizations, empires. They made it a mirror for Earth's anxieties and ambitions. And then the spacecraft arrived, and the mirror cracked. Mariner 4 crossed the void in 1964 and 65 and returned 22 grainy images of a cratered, lifeless, airless wasteland. Mars was not a living world. It was a frozen desert under a sky thinner than any mountain summit on Earth. The atmosphere, mostly carbon dioxide, less than 1% as dense as ours, offered no protection against radiation, no warmth, no breathable air. The temperature at the equator might briefly touch 0 degrees Celsius on a summer afternoon, and then plunge to minus 125 Celsius overnight. The dream did not die. It just grew harder. And harder dreams require harder thinking about what it actually takes to get there, survive there, and the question that changes everything: get back. The distance between Earth and Mars is not fixed, it breathes. At their closest approach, called opposition, the two planets sit roughly 55 million kilometers apart. At their farthest, they are separated by more than 400 million kilometers. The average, accounting for the full range of their orbital dance, is about 225 million kilometers. No human being has ever traveled more than about 400,000 kilometers from Earth. That was the Apollo program. 12 men who walked on the moon and returned safely, the farthest any member of our species has ever ventured from the planet that made them. The distance to Mars is roughly 575 times greater than the distance to the moon. Not 575% greater. 575 times. The difference is not just in kilometers. It is in time, in isolation, in radiation exposure, in the weight of every kilogram of food, water, oxygen, fuel, and equipment that has to be launched off Earth and carried across the void. A mission to the moon, at its fastest, takes about 3 days one way. A mission to Mars, using the most efficient orbital trajectory currently available to us, a Hohmann transfer orbit that arcs between the two planets when their positions align correctly, takes somewhere between 6 and 9 months. One way. The crew would spend between 6 and 9 months in transit to Mars. If the mission planned for a return, they would then need to wait on the Martian surface for roughly 500 to 600 days, nearly a year and a half, until the planets aligned again for the return journey home. Then, another 6 to 9 months back. The total duration of a conventional round-trip Mars mission, from Earth departure to Earth arrival, is somewhere between 2.5 and 3 years. Every single day of that mission has to be fed, watered, breathed, and planned for. The mass required to sustain that mission is staggering. And mass, in spaceflight, is everything. To understand why returning from Mars is so difficult, you have to understand a concept that rocket engineers call the tyranny of the rocket equation. It was first formalized in the early 20th century by a Russian schoolteacher named Konstantin Tsiolkovsky, who derived a mathematical relationship between a spacecraft's change in velocity, the exhaust velocity of its engine, and the ratio of its starting mass to its ending mass. The equation is elegant. Its implications are brutal. To change your velocity by a certain amount in space, you need propellant, but that propellant has mass. And carrying that mass means you need more propellant to carry it, which adds more mass, which requires more propellant. The relationship is exponential, not linear. To launch a spacecraft off the surface of Earth, you need to accelerate it to roughly 11 kilometers per second to escape Earth's gravity well entirely. That is why a rocket that weighs thousands of tons on the launch pad delivers a payload of just a few tons into deep space. Most of the mass is propellant. Most of the propellant burns just to lift the propellant above it. Now apply that same logic to Mars. To land on Mars, you are dealing with a gravity, well, roughly 38% as strong as Earth's. That is significant but not trivial. To lift off from Mars and achieve orbit, you need to reach roughly 5 kilometers per second. That requires fuel. That fuel has to be brought from Earth, or manufactured on Mars itself. If it is brought from Earth, every kilogram of fuel you need on the Martian surface has to be launched off Earth first, which means you need even more fuel to carry that fuel across the void. The numbers compound ferociously. Studies published by NASA and independent aerospace researchers have estimated that a fully fueled Mars ascent vehicle, just the spacecraft component, needed to lift a crew off the Martian surface and into orbit would itself weigh tens of tons. Getting that vehicle to Mars requires launching it from Earth. Getting it off Earth requires a rocket of extraordinary power. Getting that rocket off the ground requires propellant measured in thousands of tons. This is why the return trip is not simply twice the difficulty of going. It is many times more complex, more expensive, and more massive. And this is why the question of returning from Mars is not a trivial engineering detail to be sorted out later. It is the central challenge around which every realistic Mars mission design must organize itself, from the very first line of calculations. There is a phrase that gets used carefully in aerospace engineering circles: in situ resource utilization. It means making what you need from what is already there. And it represents the primary hope for ever returning from Mars without carrying all the return propellant from Earth. Mars has something enormously useful in its thin, frigid atmosphere: carbon dioxide. The Martian atmosphere is about 95% carbon dioxide. And carbon dioxide, combined with water, can be chemically processed to produce methane and oxygen, two of the most practical rocket propellants currently available. The reaction is called the Sabatier process, named after the French chemist who described it in the early 20th century. Feed carbon dioxide and hydrogen into a heated reactor, and it produces methane and water vapor. The water can be electrolyzed, split by electricity into hydrogen and oxygen. The hydrogen feeds back into the Sabatier reactor. The methane and oxygen accumulate as rocket propellant. SpaceX's Starship rocket is being designed specifically to run on methane and liquid oxygen. This is not a coincidence. The stated rationale for that propellant choice included, from the beginning, the fact that methane and oxygen can be produced from Martian resources, enabling in-principle return missions without bringing all the propellant from Earth. The vision is that a propellant production plant would be sent to Mars ahead of any crewed mission, running autonomously on Martian carbon dioxide and whatever subsurface water ice can be extracted, slowly building up a supply of return fuel over the years before any humans set foot on the surface. In principle, it works. The chemistry is sound. The question is whether the engineering can be made reliable enough, at sufficient scale, in the Martian environment, using hardware that has spent 6 to 9 months in deep space before it was ever asked to produce a single kilogram of propellant. The Mars Oxygen In Situ Resource Utilization Experiment, called MOXIE, was included on the Perseverance rover specifically to test a small-scale version of this concept in the actual Martian environment. MOXIE successfully produced oxygen from the Martian atmosphere in a series of tests conducted between 2021 and 2023. At its best performance, it produced about 10 grams of oxygen per hour. To fuel a crewed ascent vehicle for a single Mars launch, you would need something in the range of 25 tons of liquid oxygen. The scaling factor between MOXIE's best performance and what a crewed mission would require is on the order of 25,000 times. That scaling gap is not impossible to bridge in principle. But bridging it requires hardware that has not yet been built, landed on Mars, or demonstrated at anything close to mission-relevant output. And hardware that has not been tested in the actual Martian environment carries uncertainty that mission planners cannot fully eliminate through any amount of Earth-based simulation. The Martian environment has a way of defeating assumptions. The Viking landers in the 1970s discovered that Martian soil contains perchlorates, reactive chemical compounds that were not predicted by any model before the landers touched down. The Opportunity rover's final end came not from mechanical failure but from an unpredicted global dust storm that lasted far longer than any recorded previously, depriving the rover's solar panels of sunlight until its batteries went flat permanently. Perseverance's helicopter Ingenuity, intended as a brief technology demonstration lasting a few flights, outlasted its initial mission parameters by years, partly because the Martian atmosphere turned out to be slightly denser at the landing site than worst-case planning models had assumed. Mars rewards careful engineering. It also routinely surprises it. Any plan that depends on in-situ propellant production working at full capacity, without sustained failure, precisely when a crew needs it, is a plan that requires an exceptional degree of demonstrated, not modeled, reliability. That demonstration will take years of operation on Mars before any crew can bet their lives on the result. And those years push a fully conventional round-trip mission, one where the ascent vehicle is fueled and ready when the crew arrives considerably further into the future than optimistic timelines suggest. The problem of returning from Mars is not only about fuel. It is also about the human body and what happens to it in the specific combination of environments a Mars mission creates. The human body was shaped by millions of years of evolution on the surface of a planet with one specific gravity, one specific atmospheric pressure, one specific magnetic field, and one specific level of radiation exposure. Remove any of those parameters, and the body begins to adapt in ways that are not always benign. Remove several at once for an extended period, and the adaptations compound in ways that are still being characterized. In 6 to 9 months of transit to Mars, a crew will experience weightlessness continuously. Within days of entering microgravity, the cardiovascular system begins to redistribute fluid toward the upper body and head. The heart, facing less gravitational resistance, begins to reduce its output and gradually shrink. Muscles begin to atrophy because they are no longer required to work against gravity continuously. Bone density falls. Studies of long-duration spaceflight on the International Space Station have documented bone density losses of roughly 1 to 2% per month in load-bearing bones, even with dedicated exercise countermeasures that consume up to 2 hours of every crew member's day. After 6 months in microgravity, returning astronauts frequently cannot stand up without assistance. Their balance systems are disrupted. Their hearts are weaker. Their muscles have thinned noticeably. They recover, mostly, over weeks and months back on Earth. But the recovery depends on returning to Earth's gravity. And the recovery happens on a planet with hospitals, specialists, rehabilitation facilities, and everything else a technological civilization has built to support the health of its members when they need it most. On Mars, following a 6 to 9 month transit in microgravity, the crew lands in 38% gravity, not zero gravity, which would at least spare them load-bearing demands while their bodies begin adjusting. Not 1 gravity, which would begin stimulating recovery. Something in between, enough to demand physical effort from systems that have been weakening for months, not enough to fully stimulate the bone formation and muscle maintenance that those systems need to rebuild. No human being has ever spent extended time in 38% gravity. The moon landings offered a glimpse of 1/6 gravity, but only for a few days at most before the crews returned home. What the first Mars crew's bodies will be doing during a year and a half of Martian gravity, following months of weightlessness, is genuinely unknown in a way that cannot be resolved by any simulation or terrestrial analogy. Vision impairment has emerged as another serious concern from long-duration spaceflight, one that was not well understood until astronauts began returning from extended station stays with persistent visual changes. A significant percentage of astronauts who have spent 6 or more months on the International Space Station have experienced changes to their vision, in some cases lasting, in some cases progressive, associated with a condition called spaceflight-associated neuroocular syndrome. The proposed mechanism involves elevated intracranial pressure caused by the fluid shift in microgravity, which over months gradually alters the shape of the optic nerve sheath and potentially the globe of the eye itself. How the Martian gravity environment interacts with this process, whether the partial gravity is sufficient to prevent progression, or whether it merely slows an inevitable change, is unknown. An astronaut who arrives on Mars with already degraded vision from the transit, and who then spends a year and a half in partial gravity before attempting a return transit, may have vision significantly worse than when they left Earth. In a mission environment where every task requires precise physical manipulation of life support equipment, navigation through a hostile exterior environment, and careful operation of complex machinery, vision is not an optional faculty. It is a survival requirement. And then there is radiation. Earth's magnetic field is a shield. It deflects the constant stream of charged particles that pours from the sun, and it deflects the more energetic cosmic rays that arrive from outside the solar system entirely. The International Space Station, orbiting at roughly 400 kilometers altitude, sits just inside the outer edge of that magnetic protection. Astronauts on the station receive elevated radiation doses compared to Earth's surface, but the protection of the magnetic field keeps the exposure within a range that is manageable for missions of 6 to 12 months. Beyond Earth's magnetic field, in the void between planets, the protection disappears entirely. The radiation environment in interplanetary space consists of 2 main components. The first is solar energetic particles, intense bursts of protons and heavier ions ejected during solar flares and coronal mass ejections on the sun's surface. These events can be extremely powerful and can deliver significant radiation doses to anything in their path within hours of a solar event. In deep space, without adequate shielding, a major solar energetic particle event could cause acute radiation illness in a crew that was not sheltered, potentially severe enough to incapacitate crew members at a moment in the mission when their full function is most critical. Mission planners address this with storm shelters, designated regions of the spacecraft with the maximum available shielding material, typically involving water tanks, polyethylene panels, and dense equipment positioned around the crew rest area, where the crew retreats when solar activity alerts are issued. The second component is galactic cosmic rays, extraordinarily high-energy particles that originate outside the solar system, accelerated to near-light speed by supernova remnants and other energetic astrophysical events throughout the galaxy. These particles are not well stopped by practical shielding materials. When they strike matter, including human tissue, they produce secondary particles through a cascade of nuclear reactions. And in some material configurations, the secondary radiation behind the shielding can actually be worse than the primary radiation in front of it. This counterintuitive property, sometimes called the shielding paradox, means that simply adding mass between the crew and galactic cosmic rays is not a straightforward solution. The only truly effective mitigation is shortening the time spent in the high-radiation interplanetary environment. The total radiation dose a crew would receive during a round-trip mission to Mars 6 to 9 months each way. Plus, the surface stay is estimated to fall somewhere in the range of 800 to 1200 millisieverts over the full mission, depending on solar activity levels during the mission and the specific shielding configuration of the spacecraft. NASA's career radiation limit for astronauts is set at a level corresponding to a 3% increased lifetime risk of a fatal cancer outcome, which translates to a range of roughly 600 to 1200 millisieverts, depending on the astronaut's age and biological characteristics. A conventional round-trip Mars mission would bring many crew members to or near their career limit in a single mission. This has prompted some researchers to propose that early Mars mission crews should consist of older astronauts, people in their 50s or 60s, whose shorter remaining life expectancy. Differently responding tissues change the risk profile in a way that makes the same radiation dose more acceptable from a mission planning standpoint. The ethics of this proposal are complex. The underlying biology is real. On the Martian surface itself, the radiation environment improves compared to deep space. Mars does have an atmosphere, however thin, and it provides some shielding. Surface measurements from the Curiosity rover's radiation assessment detector found Martian surface radiation running at a level significantly lower than deep space interplanetary transit, though still many times higher than Earth's surface background. The more serious concern for surface operations is solar energetic particle events. Mars has no significant global magnetic field. The planet lost its internal dynamo, the convective motion in its iron core that once generated a planetary magnetic field billions of years ago, when the core cooled enough that the process could no longer sustain itself. Without that field, solar energetic particle events reach the Martian surface with minimal deflection. The thin atmosphere absorbs some lower energy particles, but a major event could deliver a significant radiation dose to any crew member not sheltered behind sufficient material. This means that a surface habitat on Mars needs not just living space and laboratory space, but dedicated radiation shelter space, and that space needs to be reachable from wherever the crew is working when an alert goes out. Every kilogram of shielding material built on Mars has to come from somewhere, which means it depends on the same in situ resource utilization that propellant production depends on. The radiation problem connects to the case for a one-way mission in a way that is not immediately obvious. If the transit is the most radiation-intensive phase of the full mission, which the dosimetry data consistently suggests, then a mission profile that eliminates the return transit eliminates roughly half the total deep space radiation dose the crew receives across the full mission duration. A crew that goes to Mars and stays on Mars absorbs one transit dose, plus whatever surface dose accumulates over their years there, but never takes the second transit dose. Given that the transit doses account for the majority of the career limit used up by a round-trip mission, this is not a trivial difference. From a pure radiation biology standpoint, A permanent one-way mission may actually be the less radiologically costly option over a sufficient time horizon. There is a concept in mission planning called the minimum viable mission, a design approach that asks honestly, what is the least you can send to accomplish the core objectives, and what does that mission actually look like when you are not padding the architecture with aspirations? For a Mars mission, that question forces a confrontation with the return problem almost immediately. If the return trip requires a fully fueled Mars ascent vehicle ready and waiting when the crew arrives, then that vehicle has to be pre-positioned years before any crew departs. It has to survive the interplanetary transit. It has to survive landing in a high-energy entry through a thin atmosphere with no ocean to cushion the final descent. It has to survive the Martian environment, temperature swings, dust, cosmic radiation for years of autonomous operation before any crew is anywhere near it. Its propellant production systems have to run reliably during that entire waiting period without a human technician within tens of millions of kilometers to fix anything that breaks. And when the crew is finally ready to ascend, every system, engines, fuel lines, avionics, guidance has to work correctly the first time, because there is no second chance, no backup vehicle, and no repair mission coming in any time frame that could help. The history of spaceflight is a history of carefully managed failure modes, redundant systems, abort options, safe modes. The culture of contingency planning is deep in the DNA of human spaceflight because the margin between a successful mission and a catastrophic one is frequently thinner than anyone would prefer. The Apollo lunar module had a single ascent engine, one engine, no backup. Everyone involved knew that if that engine failed to ignite, the mission would end on the lunar surface. The engine worked every time. But the margin for error on the surface of a planet at the far end of a radio signal that takes up to 24 minutes one way, where real-time intervention from mission control is a physical impossibility, is not thin. It approaches zero. Every contingency that might be addressed with a quick call to mission control, every decision that a flight director might make in real time for an Apollo crew, becomes a decision that the Mars crew has to make for themselves, with whatever information and equipment they carry. With the full knowledge that whatever choice they make, they will live or not live with the consequences before Earth even knows there was a problem. This communication delay has consequences that go well beyond operational logistics. A medical emergency on the surface of Mars, a serious traumatic injury from a surface excursion, a cardiovascular event, a sudden and severe neurological symptom cannot be triaged by Earth-based physicians in real time. A crew member who needs immediate intervention cannot receive guidance from a trauma specialist when the signal takes up to 24 minutes just to arrive on one end. The crew must manage everything themselves. With the medical training and equipment they carried from Earth, making clinical judgments that on Earth would involve a team of specialists with hospital infrastructure supporting every decision. This requirement has driven the medical training for Mars mission crew concepts to a level far beyond anything required for low Earth orbit missions. The earliest Mars crews, in essentially every serious architectural concept, must include at least one highly trained physician, ideally a surgeon, with the skills to perform emergency procedures in a habitat environment with minimal equipment. They must carry enough pharmaceutical stock and medical supplies to manage years of potential illness and injury without resupply. They must be trained to manage situations that no amount of preparation can fully script in advance. Because on Mars, the doctor is whoever you brought with you. This is where the economics and the physics and the physiology all converge on the same uncomfortable conclusion. The hardest part of going to Mars is coming back. Not because getting there is easy, it is not, but because the return trip requires everything the outbound journey required. plus a fully operational propellant production facility on Mars performing reliably for years, plus a functional ascent vehicle that has survived years of Martian conditions, waiting for a crew it doesn't know is coming, plus a trajectory window that only opens for a few weeks every 26 months, plus a crew that is physically capable, after years of radiation exposure and partial gravity, of making the journey home, and then spending another 6 to 9 months in microgravity before they can finally return to the planet that built them. Studies estimating the mass budget for a return-capable Mars mission, compared to a one-way settlement mission, consistently arrive at factors of 2 to 5 times the required launched mass. That is not a small multiplier. In spaceflight, mass is money, and money is time, and time is institutional will. The cost of launching mass into orbit, let alone sending it to another planet, runs into thousands of dollars per kilogram, with even the most optimistic projections for near-term launch vehicle economics. A mission that requires 5 times the mass costs many times more to execute. And execution requires not just money, but the sustained organizational commitment of institutions whose planning horizons rarely extend without revision beyond a decade. NASA has been planning Mars missions seriously, with funded studies and published architecture documents since the 1970s. In 1989, President George H.W. Bush called for a human mission to Mars by 2019, a 30-year program called the Space Exploration Initiative. It was never funded. In 2004, President George W. Bush announced the Vision for Space Exploration, which included Mars as a long-term destination. The program was restructured before it was completed. In 2017, Congress directed NASA to develop a roadmap for a crewed Mars mission in the 2030s. The timeline has continued to shift. None of this reflects a lack of desire or technical understanding. It reflects the structural difficulty of committing the necessary resources to a program whose full costs materialize over timescales that exceed any single political administration, whose benefits are real but distant, and whose mass and complexity requirements remain formidable regardless of how the plan is organized. Private spaceflight has changed the calculus somewhat. The introduction of genuinely new, competitive, commercially motivated launch capability has reduced costs and increased launch rates in ways that were not plausible even 15 years ago. But the fundamental physics has not changed, and the fundamental engineering challenges of keeping people alive for years in an environment as hostile as Mars have not changed either. The mass problem is less severe than it was. It is still severe. This is the context in which serious mission architects have begun asking a question that sounds, on first hearing, like a kind of surrender. What if the first humans to reach Mars do not come back? The question is not new, and it is not asked carelessly. It was raised explicitly in peer-reviewed scientific literature in 2012, when researchers Dirk Schulze-Makuch and Paul Davies published a paper in the Journal of Cosmology titled "To Boldly Go, a One-Way Human Mission to Mars." Their argument was not that returning was impossible. It was that requiring return as a condition of the first mission was adding complexity and cost at a scale that was preventing the mission from ever happening, and that a human presence on Mars, even a permanent one with no return option, was more valuable to the long-term future of the species than a return-capable mission that remained perpetually deferred. The analogy they drew was to human migration history, to the people who crossed land bridges, boarded boats into unknown waters, followed coastlines or mountain passes into territories no one had mapped, knowing they would not be returning to where they had come from. Many of the most consequential human expansions across the surface of this planet were one way. People left not knowing what was ahead, motivated by necessity or curiosity, or the simple understanding that whatever lay on the other side was worth the price of not going back. The proposal generated substantial response across the scientific community, from serious academic engagement to deep ethical concern. The ethical concerns are real. But the most commonly raised objection, that people could not meaningfully consent to a permanent journey, is not the strongest version of the argument. Clearly, they could consent. The response to calls for volunteers from Mars mission initiatives has consistently demonstrated that enormous numbers of people would willingly and enthusiastically accept a one-way passage to Mars. The deeper ethical question is whether consent given before an experience can be meaningfully informed about what that experience will feel like from the inside. A person who volunteers to go to Mars permanently has never been to Mars. They have imagined it, trained for it, thought carefully about it, prepared as thoroughly as any human being can prepare for something no human being has done. But they have not felt the weight of the permanent reality of it. They have not lived through the moment, perhaps months or years after arrival, when the intellectual understanding that they will never return becomes something experienced rather than merely known. Some researchers who study irreversible decisions argue that this gap between anticipated and experienced reality is ethically significant. The counter-argument is that this gap is present in essentially every major irreversible commitment a human being makes. Careers, relationships, children, migration to a new country. All of these are chosen before the full reality of them is experienced. The capacity to make meaningful commitments in the face of irreducible uncertainty is not a failure of agency. It is what agency consists of. The Mars One project, a Netherlands-based private initiative that launched in the early 2010s, proposed exactly this model of permanent one-way settlement and claimed to have received more than 200,000 initial interest applications from people expressing willingness to go. The organization ultimately collapsed financially, unable to secure the sustained investment its ambitious architecture required. This was evidence of the difficulty of the funding problem. It was not evidence that people were unwilling to go. The barrier to the first Mars mission has never been human willingness. It has always been the engineering and the economics and the institutions required to make the journey possible. The physics of a one-way mission differ from a round-trip mission in ways that cascade through every level of the design. Remove the return requirement, and the entire architecture changes. The most immediate effect is on the mass budget. Without a Mars ascent vehicle, without the propellant production infrastructure to fuel it, without the orbital rendezvous and docking systems required to rejoin an Earth-return spacecraft waiting in Mars orbit, the mass that needs to be landed on the surface drops significantly. That mass can be redirected toward the things that actually matter for long-term survival. Habitat volume. People need space to live without going psychologically sideways over years of confinement. Radiation shielding built into the habitat structure and available as a shelter for solar particle events. Food production systems, greenhouses, or controlled environment growing facilities capable of producing a meaningful fraction of the crew's caloric needs. Water recycling and extraction infrastructure, closed-loop systems that reduce the dependence on resupply. Scientific equipment. The instruments and tools that make the scientific return of the mission commensurate with its cost. Power generation hardware, a combination of solar panels and nuclear reactors that can keep everything running, regardless of Martian dust conditions. Spare parts, redundant systems, and manufacturing capability, because on Mars, whatever breaks, you fix. A one-way settlement mission does not require less investment than a round-trip mission. In some respects, it requires considerably more because the infrastructure has to be designed for indefinite operation rather than for a fixed mission duration. But the investment is concentrated differently in permanence and resilience rather than in the mechanical complexity of returning home. A one-way mission also liberates the trajectory options. Round-trip missions are tightly constrained by planetary alignment windows that recur every 26 months. A settlement mission is not constrained in the same way. Resupply missions can follow at whatever frequency resources allow. Additional crew can arrive when surface infrastructure is ready to support them. The settlement grows at the pace that technology and economics permit, rather than being locked to the unyielding clock of a fixed return window. The technology required for long-term survival on Mars is largely the same technology required to support a return trip from Mars. The difference lies in what the architecture prioritizes. A round-trip mission prioritizes getting home. A settlement mission prioritizes building something that can last indefinitely. Both require life support systems that can function for years with minimal intervention. Both require power generation that can survive Martian dust events. The global dust storm of 2018 enveloped virtually the entire Martian surface for months, reducing solar irradiance at the surface to levels that could not sustain a power system dependent on solar panels alone. That storm effectively ended the operational life of the Opportunity rover by starving its batteries of the sunlight they needed to recharge. A crewed settlement cannot be vulnerable to the same failure mode. Nuclear fission reactors, compact, reliable, independent of atmospheric conditions, are considered essential by essentially every serious Mars mission architect. NASA's Kilopower project developed and successfully tested a small nuclear fission reactor concept, specifically designed for planetary surface applications. A 10-kilowatt Kilopower unit can power a small habitat indefinitely, regardless of how much dust fills the Martian sky. Scaling up to the tens or hundreds of kilowatts a growing settlement would eventually require is an engineering challenge. It is not a physics impossibility. Water is the next critical resource. And Mars has it. Significant quantities of water ice are locked in the polar caps and in subsurface deposits distributed across broad mid-latitude regions. The SHARAD and MARSIS radar sounders aboard Mars Reconnaissance Orbiter and Mars Express have mapped these subsurface ice deposits in detail, finding that some of the most accessible appear within a few meters of the surface at latitudes between 30 and 50 degrees in both hemispheres. Extracting that ice, melting it, and purifying it for use is achievable with well-understood engineering. Combined with water recycling systems already deployed on the International Space Station that recover and reuse nearly 90% of the water vapor from crew respiration, perspiration. A settlement could establish a largely closed water cycle that requires only periodic extraction from subsurface ice to compensate for losses. Food production, at a self-sustaining scale, is more complex and less solved. The International Space Station currently grows no meaningful quantity of food. Every calorie consumed by its crew arrives on resupply missions, packaged and processed on Earth, launched at enormous cost, carried across 400 kilometers of atmosphere and vacuum. A Mars settlement cannot function this way. The transit times are too long and the dependency too fragile. Controlled environment agriculture, growing food in sealed, pressurized, artificially lit, growing facilities using hydroponic or aeroponic systems is the most developed technology available for off-world food production. It is energy-intensive, requiring sustained input for lighting, climate control, and water management. But for a settlement with access to nuclear power, the energy is available. The choice of crops matters. High-calorie, nutritionally complete crops with reliable yields and short production cycles have been studied in the context of space agriculture for decades. Potatoes, sweet potatoes, soybeans, legumes, and various leafy greens rank well on the relevant criteria. Getting those crops to produce consistently in a Martian growing environment, accounting for the slightly different light spectrum from artificial sources. The gravity level. The challenging starting material of Martian regolith is not a solved problem, but it is a tractable one. Martian soil contains perchlorates that are toxic to human biology, but can be removed through washing and treatment. It lacks the microbial community that makes Earth's soil productive, which means building viable growing media requires either importing microorganisms to seed soil biology or relying on liquid nutrient solutions produced in situ. Neither is a trivial undertaking at the scale of feeding a crew. Neither is physically impossible. The direction of technology development in controlled environment agriculture on Earth, driven by population growth, water scarcity, and the economics of year-round food production in harsh climates, has been consistently toward greater reliability, lower energy use per unit of food produced, and systems that can operate with less technical expertise per unit of output. Every advance in Earth-based vertical farming or greenhouse technology is potentially applicable to a Mars-growing facility. The problems are hard. They are not harder than the problems that have already been solved to get to this point in the story. The psychological architecture of a permanent Mars settlement is perhaps the least studied and most critical element of whether it actually works over timescales longer than a few months. The history of long-duration, isolated environments offers some guidance, and none of it maps cleanly onto what a permanent Mars presence would be. Submarine crews spend weeks or months confined in tight spaces, cut off from the outside world, but they know with certainty that the mission will end. Antarctic, overwintering research teams endure months of genuine isolation in extreme conditions, but they are on the same planet as everyone they love, reachable by satellite phone, eventually accessible to resupply aircraft. Long-duration space station crews experience real isolation, but their missions have fixed end dates. An emergency return is a real option if something goes seriously wrong. The psychological environment of a permanent Mars settlement combines elements of all of these with one factor that none of them share: the absence of a finite end. The settlers would not be counting down to the day they come home. The mission would not conclude. They would be building a life in a place they intend to inhabit permanently, under circumstances they cannot leave. That is a fundamentally different psychological frame from any long-duration mission in human history, and the literature on isolated, confined environments does not fully prepare anyone for it. Research into the psychology of permanent migration, people who have voluntarily left their country of origin with no intention of returning, offers some more relevant insights. Strong social bonds within the new community, clear and meaningful shared purpose, demanding and varied work, genuine agency over day-to-day decisions, and connection to an identity that transcends physical location all appear to support psychological resilience in people who have chosen permanent departure. A Mars settlement would need all of these factors deliberately designed into its social and operational structure. The selection of crew not just for technical competence but for psychological compatibility under extreme stress, conflict resolution capacity, adaptability to unexpected circumstances, and the motivational profile suited to permanent commitment rather than time-limited service is as important as any engineering specification. Research on small group dynamics in isolated and confined environments consistently identifies interpersonal conflict as one of the primary risks to mission success. In a setting where there is no way to leave, no possibility of stepping outside for space from the people around you, no option of a quiet walk in a park or a few hours of genuine solitude, managing interpersonal dynamics is not a soft organizational consideration. It is a hard operational survival requirement. The Mars 500 study, conducted between 2010 and 2011, confined 6 volunteers in a facility near Moscow, simulating a 520-day Mars mission. Among the findings that emerged from the study, sedentary behavior increased significantly and progressively over the mission duration, particularly during the simulated surface and return phases. Sleep disturbances were widespread and tended to worsen rather than stabilize over time. One participant largely withdrew from group social engagement during the simulated return transit, sleeping far more than others and disengaging from planned activities. These were not dramatic crises that threatened the simulation. They were indicators of slow, Cumulative psychological erosion, the kind of wear that would need to be actively and deliberately addressed in a real mission of significantly longer duration. A permanent Mars settlement would need to be designed with psychological health as a primary engineering constraint, not an afterthought. Work schedules that provide rhythm and meaning. Social structures that manage conflict without suppression. Communication with Earth that maintains connection without creating dependency. Physical environments that are as humane as resource constraints allow, because humans do better with light, with color, with space, with the ability to sometimes be alone, in ways that are not luxuries. They are requirements. The technological trajectory toward Mars is accelerating. SpaceX's Starship rocket, a fully reusable launch system designed from the beginning, with Mars colonization as its stated ultimate objective, has been under development and active testing throughout the early 2020s. The vehicle is designed to carry substantial payloads to Mars, running on methane and liquid oxygen propellants, compatible in principle with in-situ Martian production. It is intended to be refueled in Earth orbit before beginning the interplanetary transit, enabling it to carry far more mass toward Mars than any single direct launch from Earth could achieve. If Starship, or a vehicle with similar capabilities developed by other programs, achieves the reliability and cost performance its designers intend, the mass budget constraints that have dominated Mars mission planning for decades begin to ease, not disappear. Ease. Reusability changes the economics of spaceflight in a way that matters enormously for Mars. If the same vehicle can be flown many times rather than being expended on each launch, the cost per kilogram to orbit can fall by orders of magnitude compared to the expendable rockets that defined the 20th century. Falling costs change what is practical. They do not change the rocket equation. They do not change the radiation environment. They do not change the complexity of keeping people alive for years on the surface of a hostile world. But they change what is economically achievable within a planning horizon that institutions can actually commit to. NASA's Moon to Mars architecture, updated and revised across administrations, maintains human Mars presence as a long-term program objective and has invested in key enabling technologies, advanced power systems for planetary surfaces, propellant production demonstrations, long-duration life support systems, and the deep space habitation technology that any interplanetary crew would require. The vision articulated across multiple agencies and private companies, whatever their specific disagreements about timelines and architectural choices, is broadly consistent in its structure. Uncrewed cargo missions first, establishing supply caches and testing critical systems autonomously. Then, crewed missions, initially short surface stays to validate the technology and establish the first human presence. Then longer stays. Then permanent occupation. The timeline for each of these steps is genuinely uncertain. The direction of travel is not. The first humans to reach Mars will face something that no mission document, no training simulation, no amount of preparation can fully replicate before they get there. They will step out onto the surface of another planet and look up at a sky that is not blue. The Martian daytime sky takes on hues of butterscotch and dusty pink near the horizon, from fine suspended particles that scatter light differently than Earth's atmosphere does. Near the zenith on a clearer day, the sky can shift toward a more bluish tone, but it is a blue that no human settlement in the history of the species has ever looked up at before. The sun in that sky will be visibly smaller and colder looking than the sun seen from Earth, the same star, but viewed from farther away, reduced to a bright point that still delivers enough energy to generate power, but no longer warms the face in the way a human being has been wired by evolution to expect warmth from the sky. The horizon will be closer than Earth's. Mars is a smaller planet. Standing in a flat region on Mars, The visible horizon is roughly 3 kilometers away, rather than the approximately 4.5 kilometers an adult of average height would see on level ground on Earth. The silence would be almost absolute. The Martian atmosphere is too thin to carry sound efficiently at the frequencies humans hear most clearly. The wind in a significant dust storm still moves fast, but it has almost no force because the air is so sparse. Astronauts inside a habitat on Mars would hear almost nothing of the exterior environment, only the sounds of their own equipment, their own breathing, and the lives of the people around them. The landscape would be geologically remarkable in ways that decades of robotic exploration have only partially conveyed. Ancient impact craters, some of them so ancient their rims have been worn down to gentle ridges. Volcanic plains of dark basalt stretching toward a horizon that is always 3 kilometers away. Canyon systems that dwarf anything on Earth in scale. The Valles Marineris stretches for roughly 4,000 kilometers from end to end, reaching depths of up to 7 kilometers in places. The Olympus Mons Shield volcano rises approximately 22 kilometers above the surrounding plains and spans roughly 600 kilometers at its base, a geological structure so large that if you stood at its center, you would not be able to see its edges from any direction. The horizon would hide them. Mars was not always the frozen desert that the rovers have been crossing for decades. The evidence is preserved in the surface itself. River valleys cut into ancient highlands, preserved for billions of years in a cold world too dry to erode them further. Minerals that form only in the presence of liquid water, identified by orbital spectrometers and ground-level drilling. Sedimentary layers in the Gale crater, drilled and analyzed by Curiosity, representing millions of years of lakebed deposition. Mars was once wet. It was once warm enough for liquid water to persist at the surface. Whether it was ever host to life, microbial, simple, ancient, is one of the most important unanswered scientific questions our species has ever formulated. The first people on Mars will be in the best position in the history of the species to pursue that question. They will have mobility that no rover can match. They will have cognitive flexibility and contextual scientific judgment that no automated system can replicate. They will be able to recognize something unexpected in a rock exposure and examine it carefully, to decide in the moment that what they are looking at matters more than where they were heading, to do the kind of science that requires a mind on the spot rather than instructions sent from millions of kilometers away, with a 20-minute delay between question and response. The scientific return of a human Mars mission is not simply the scientific return of a rover mission multiplied by some factor. It is categorically different. Humans do things in the field that machines cannot do. And Mars is a field of extraordinary richness, waiting for someone with the capacity to understand what they are seeing. There is a number that appears in serious Mars settlement literature when researchers try to estimate the transition from initial foothold to genuinely self-sustaining presence. The rough estimate, most commonly cited, is that a settlement might reach functional self-sufficiency, the ability to sustain itself without continuous resupply from Earth, with a population somewhere between 100 and 1,000 people. The reasoning is about the minimum complexity of a technological civilization. A settlement of 10 people cannot maintain all the skills, knowledge, and manufacturing capability required to keep its systems running, manage medical care, produce food, conduct science, repair everything that breaks, and replace everything that wears out. A settlement of 100 begins to approach the minimum diversity required. Several hundred achieves genuine resilience, enough redundancy and critical skills that the settlement can absorb losses and unexpected demands without collapsing. The first mission will be a handful of people. 4, perhaps 6, perhaps 8. Their job will not be to achieve self-sufficiency. Their job will be to survive, to learn, to demonstrate that human beings can live and work on the surface of Mars, and to build with their work, their observations, and their presence, the foundation that the missions following them can build on. Whether they return to Earth or remain on Mars, the significance of their journey is the same. They will have crossed the gap between worlds. They will have demonstrated that a human being can breathe recycled air under an alien sky and do meaningful work and stay alive. And everything that follows everything will be built on what those first few people managed to accomplish in the frozen, irradiated, beautiful, violent desert that will be the first world beyond Earth that any human being has ever called home. The conversation about a one-way Mars mission is not new. It has been circulating quietly and with varying degrees of seriousness among space scientists and mission architects since at least the 1990s. But it acquired a different quality around 2012, when Dirk Schulze-Makuch and Paul Davies, a planetary scientist and a theoretical physicist, published a paper in the Journal of Cosmology, arguing not just that a one-way mission was technically feasible, but that it was the logical first step. Their argument was not sensational. It was careful. They pointed out that most of the mass, most of the cost, and most of the risk in a conventional round-trip Mars mission was concentrated in the return half the ascent from Mars. The trans-Earth injection burn, the months in transit back, the re-entry and landing on Earth. Remove the return leg, they argued, and you do not just simplify the mission, you transform it. The vehicle that reaches Mars can carry more habitat instead of return propellant. It can carry more food, more equipment, more redundancy. The crew does not have to preserve a functional ascent vehicle and its fuel supply through years of Martian surface operations, protecting systems they might never need to use from dust, radiation, and mechanical degradation. They can focus entirely on the work of surviving, exploring, and establishing a permanent presence. Schulze-Makuch and Davies were careful to note that one way did not mean abandoned. It meant pioneer. The commitment of civilization was to continue sending missions more crew, more supplies, more equipment, until a genuine settlement existed. The first crew went ahead, prepared the ground, and waited for reinforcements. This model had been used by human civilization many times before. It was how the Polynesian expansion across the Pacific worked, not scouting trips that returned to report, voyages of settlement, where the people who left understood that the world they were heading toward was where they intended to build their lives. The pushback against the Schulze-Makuch and Davies proposal was immediate and predictable. Critics called it unethical to send people to a place they could not leave. They called it a death sentence dressed up in scientific language. They questioned whether any national space agency or reputable private organization could recruit volunteers, obtain regulatory approval, and withstand the public and political reaction. These are serious objections. They deserve serious engagement rather than dismissal. But they rest on an assumption that deserves examination. The assumption that remaining on Mars is equivalent to dying on Mars. It is not. The goal of a one-way mission is not to maroon people on a hostile world and abandon them. The goal is to establish the first permanent human outpost on another planet, staffed by people who chose to be there, supported by the rest of our civilization, and followed by more missions as quickly as the technology and funding allow. The ethics of such a mission rest on informed consent. Any person who volunteered to go would understand exactly what they were agreeing to. They would understand the risks. They would understand that the return path was not certain and not soon. They would make that choice freely, as adults, in full possession of the facts. Human civilization has a long tradition of honoring such choices. We honor soldiers who volunteer for dangerous assignments. We honor mountaineers who attempt peaks with serious mortality rates. We honor test pilots who fly vehicles that have never been flown before. The principle that free individuals may choose to accept risk in pursuit of something they believe is important is foundational to how our species organizes itself. The argument that no one should be allowed to make such a choice because the risk is too great or because civilization cannot bear the psychological weight of watching them go, says more about the institutions making the argument than it does about the individuals who would choose differently. The question of who would actually choose to go is one that psychologists and mission planners have been studying with increasing seriousness. The profile that emerges from that research is not what popular culture would suggest. It is not a death wish. It is not recklessness. It is not an inability to value the life being left behind. The people who score highest on psychological readiness for long-duration space missions, including permanent ones, tend to be characterized by high tolerance for ambiguity, strong internal motivation rather than external validation, deep identification with a purpose larger than personal comfort, and a particular relationship with solitude, not the inability to be alone, but the capacity to find solitude generative rather than threatening. They tend to be people for whom meaning is more important than safety, without being indifferent to safety. They tend to have processed the question of mortality more deliberately than average, not morbidly, but with a clarity about what matters and what does not. The Mars 500 study, conducted between 2007 and 2011, isolated 6 volunteers in a simulated Mars mission habitat in Moscow for 520 days, roughly the duration of a full round-trip Mars mission. They were not told they could leave whenever they wanted. The simulation was designed to be as psychologically realistic as the team could make it. What emerged from the study was both reassuring and sobering. The crew adapted. They maintained functional working relationships across most of the mission. They completed assigned tasks. They did not collapse. But the study also documented significant sleep disturbances, reduced physical activity levels, psychological withdrawal in some crew members during the return leg, and evidence of motivational decline during the long transit phases. The absence of external stimulation, no new landscapes, no meaningful changes in the environment outside the habitat, no genuine sense of forward progress turned out to be one of the harder psychological challenges to manage. On actual Mars, this dynamic would be different in important ways. There would be a genuine surface to explore. There would be work of real consequence. There would be scientific questions to pursue that had never been pursued before. The landscape, however hostile, would be endlessly varied in detail. New rock exposures, new atmospheric readings, the possibility of finding something unexpected on any given sol. Whether that difference would be sufficient to sustain the psychological health of a small crew across a multi-year mission, no one can say with certainty. But the evidence suggests that meaningful work is one of the most powerful buffers against the kinds of psychological deterioration that isolation can produce. And no Mars mission would lack for meaningful work. There is another dimension to the one-way question that does not receive enough attention in the engineering and ethical discussions. It is the question of what permanent settlement means for the long-term trajectory of the human species. The first Mars settlement, however small, however dependent on Earth for years or decades, would represent a fundamental change in the nature of human civilization. For the first time in the history of our species, we would not be a single-planet civilization. All of human existence, from the first tool-using hominid to the present day, has played out on one world. Every human being who has ever lived was born on Earth, lived on Earth, and died on Earth. Every civilization, every language, every religion, every piece of art, every scientific discovery, all of it has emerged from a single thin biosphere, wrapped around a single rocky planet, orbiting a single ordinary star. The fragility of that situation becomes obvious when you examine the history of mass extinctions. Earth has experienced at least 5 major extinction events, each one wiping out a significant fraction of the species then living on its surface. The most severe, roughly 252 million years ago, eliminated perhaps 90% of all marine species and 70% of all terrestrial vertebrate species. The most recent, 66 million years ago, ended the age of non-avian dinosaurs, and restructured the planet's ecology. In each case, the cause was something beyond the control of any organism living at the time: a massive volcanic eruption, an asteroid impact, a shift in ocean chemistry. The organisms that went extinct had no capacity to relocate. They had nowhere else to go. We do. We have the technology, in its early form, to reach another world. We have the knowledge to understand why planetary resilience matters. We have the capacity to make a deliberate choice about whether we want to remain confined to a single point of failure or begin the process of distributing the human presence across more than one world. The first Mars mission does not achieve that distribution by itself. A handful of people in a habitat on Mars does not secure the future of the species, but it begins the process. It demonstrates that the process is possible. It provides a foundation on which genuinely self-sustaining settlements can eventually be built. And in doing so, it changes the nature of the question from "can we do this?" to "how do we do this better?" That shift from a theoretical possibility to an operational reality is worth more than any individual mission profile can capture. The engineering reality of what it would take to keep those first settlers alive on Mars is worth examining in detail, because it is where the abstract argument about one-way missions meets the concrete requirements of survival. The fundamental challenge of living on Mars is not any single hostile condition. It is the intersection of many hostile conditions simultaneously, with almost no margin for error and almost no possibility of emergency resupply from Earth. The Martian atmosphere is 95% carbon dioxide. It is less than 1% as dense as Earth's atmosphere at sea level. It offers no protection against solar ultraviolet radiation, which sterilizes the surface and prevents any Earth organism from surviving unshielded in the open. It offers almost no insulation against temperature extremes. It does not carry enough oxygen to breathe. It cannot be terraformed quickly. Every moment a person spends on the Martian surface outside a pressurized habitat requires a suit that maintains pressure against a near vacuum, provides breathable air, regulates temperature against swings of 150 degrees or more, and shields the wearer from radiation levels that would deliver a significant annual dose from extended outdoor activity. The suits required for extended surface operations on Mars would need to be more capable, more durable, and more reliable than any spacesuit ever built for use on the Moon or on the International Space Station. They would need to be repairable in the field, with tools and materials available on Mars, because any suit that could not be repaired would eventually fail. And a failed suit in an environment where the outside air cannot be breathed is fatal. The habitat itself would face similar demands. It would need to maintain pressure against a Martian atmosphere that is constantly trying to equalize slowly through any imperfection in seals or joints, but constantly. It would need to provide radiation shielding, either through its own structure, through burial under Martian regolith, or through some combination of both. The regolith approach, covering the habitat with meters of Martian soil, has the advantage of using locally available material, but requires robotic excavation and emplacement before any crew arrives, and requires the habitat to be structurally capable of bearing that load. The habitat would need to recycle air, water, and as much organic material as possible, because the supply line from Earth is not a pipeline. It is a launch window that opens every 26 months. If something essential breaks and cannot be repaired and cannot wait 26 months for replacement, people die. That is the design constraint that shapes everything else. It means redundancy everywhere, critical. It means systems designed to fail safely, to degrade gracefully rather than catastrophically. It means crew members trained not as specialists but as generalists, who can respond to whatever the environment presents, who can diagnose and repair systems outside their primary expertise. who can keep the habitat functional under conditions that no training scenario fully anticipated. The power system is particularly critical. Solar power on Mars is viable, but solar panels there receive roughly 43% of the solar irradiance they would receive at Earth orbit, and during global dust storms, that fraction drops further. The 2018 global dust storm that ended the Opportunity rover's mission lasted 8 months and dropped solar irradiance to levels that could not sustain the rover's power budget. A crewed habitat, depending solely on solar power during such an event, would be in serious danger. The most credible power architecture for early Mars settlements involves nuclear fission reactors. NASA's Kilopower project demonstrated a small fission reactor concept capable of producing 10 kilowatts of electrical power continuously, regardless of solar conditions, for years of operation. A small array of kilopower-class reactors could provide the baseline power for a modest habitat, allowing solar panels to supplement the power budget during favorable conditions while ensuring survival power is always available from the fission systems. 10 kilowatts sounds modest. It is roughly the continuous power draw of a small house for a habitat with a small crew operating basic life support systems, lighting, computing, communications, and minimal science equipment. 10 to 40 kilowatts of reliable power is a functional baseline. The Martian dust, beyond its effect on solar power, presents hazards that are still not fully characterized. The fine-grained nature of Martian regolith particles, small enough to remain suspended in the atmosphere for months during global storms, means it can penetrate seals, coat optical surfaces, clog mechanical systems, and, most worryingly, interact with human lung tissue in ways that the robotics program has not yet allowed direct investigation of. Lunar dust caused significant equipment problems during Apollo despite the relatively brief surface stays. Martian dust, electrostatically charged by the thin atmosphere, may cling more aggressively to surfaces and be harder to remove. Whether long-term exposure to Martian dust in a habitat, even at low concentrations through filtration system imperfections, poses a health hazard comparable to silicosis on Earth is unknown. It is the kind of question that only years of surface operations, by people who can study their own health, will begin to answer. The food question is perhaps the most underappreciated challenge in Mars settlement planning. You can optimize resupply manifests for years without fully confronting what it means to be responsible for feeding a small group of people on a world where nothing edible grows naturally, anywhere you look. The mass per person per year for a reasonable Earth diet is roughly enough food that shipping it from Earth for even a small crew over the lifetime of a long-duration mission would consume, an enormous fraction of the available launch mass. The alternative is growing food on Mars. The Martian regolith is not soil in any meaningful agricultural sense. It contains perchlorates, chlorine-containing compounds at concentrations high enough to be toxic to most plants, and to humans who consume plants grown in it without treatment. It lacks the organic matter, the microbial communities, and the mineral balance that productive agricultural soil requires. It would need to be processed, probably mixed with materials brought from Earth or produced on Mars, and inoculated with biological communities before it could support meaningful crop production. The closed-environment agriculture experiments conducted in analog settings on Earth, the work done at the controlled environment agriculture facilities, the Antarctic stations, the various space agency habitat simulators have demonstrated that it is possible to grow meaningful quantities of food in artificial environments with relatively modest footprints. Lettuce, tomatoes, radishes, potatoes, beans, herbs, wheat, all have been grown successfully in controlled environment agriculture. The caloric density and diversity required to keep a crew healthy over years requires more space and more careful management than has been demonstrated in any analog setting yet. But the trajectory of the technology is encouraging. LED lighting optimized for plant photosynthesis has become dramatically more efficient and affordable. Hydroponic and aeroponic growing systems have matured considerably. Crop selection optimized for caloric density, nutritional completeness, growth speed, and psychological value. The joy of eating something fresh and varied matters more than mission planners typically acknowledge. In their technical documents is an active area of research. The psychological dimension of food is not trivial. In long-duration isolation studies, monotonous food, even nutritionally adequate food, becomes a source of significant psychological stress. The variety, texture, smell, and cultural meaning of food is part of how human beings sustain themselves emotionally as well as physically. The cuisine of the first Mars settlement will be constrained. It will be repetitive by Earth standards. But the effort to make it as varied and as meaningful as the constraints allow is not an optional amenity. It is part of keeping the crew functional. The communication problem deserves more attention than it usually receives in public discussions of Mars missions. The delay is not just an inconvenience. It is a fundamental change in the relationship between the crew and Earth. At the distance of Mars, radio signals travel between 4 and 24 minutes one way, depending on where the planets are in their orbits. At a typical mission phase, a crew member asking a question would wait anywhere from 8 to 48 minutes for an answer. That is not a conversation. It is correspondence. The entire real-time mission control model, the continuous voice loop between crew and ground team, the instant intervention capability when something goes wrong, the shared situational awareness that characterized both the Apollo program and the International Space Station becomes impossible at interplanetary distances. The crew on Mars will be, in an operational sense, completely on their own for every decision that cannot wait an hour. This changes crew selection. It changes training. It changes the fundamental architecture of what a Mars mission actually is. Every crew member must be capable of making medical decisions about their crewmates. Every crew member must be capable of troubleshooting and repairing systems outside their primary expertise. Every crew member must be capable of leading when their specialty is relevant and following effectively when it is not. The mission commander is not a title from mission control. It is a genuine operational role that means something in the moments when something breaks at 2 in the morning. And the person who designed the system is asleep, and Earth is 22 minutes away. The crews that succeed on long-duration Mars missions will be generalist specialists, people with deep expertise in at least one critical area and broad functional competence across many. Others, they will be people who are comfortable with ambiguity, who can tolerate not knowing whether the decision they just made was the right one, and who can function under conditions where the feedback loop on their choices is measured in months rather than minutes. The training required to produce such crews is more demanding than anything currently required for ISS missions. It would likely involve extended analog deployments in environments that approach the isolation and autonomy of Mars, Antarctic stations, desert research, outposts. Submarine missions combined with simulation exercises designed to force exactly the kinds of decisions that real emergencies produce. There is a scientific case for the first Mars mission that stands on its own, separate from the engineering arguments about mission architecture and the ethical arguments about one-way versus round trip. It is a case built around a question that has been central to human scientific curiosity since the Mariner probes first revealed what Mars actually looked like. Did Mars ever have life? The evidence that Mars was once warm and wet enough to support liquid water at its surface is extensive and compelling. Ancient river valleys cut through highland terrain that has not seen flowing water for billions of years. Massive delta fans formed where rivers once emptied into crater lakes. Evaporite mineral sequences that form when standing water evaporates slowly, leaving behind layers of sulfate and carbonate minerals that preserve the chemical record of what that water was like. organic molecules detected in ancient lakebeds by the Curiosity rover, surviving billions of years in a form that points toward chemistry compatible with life, even if it does not confirm life. Mars was wet for long enough, geological evidence suggests. Possibly hundreds of millions of years of surface liquid water in its earliest history for life to have arisen. If life on Earth is any guide to how readily it arises, given appropriate conditions, the question of whether it did cannot be answered by any robotic system currently operating or planned for near-term deployment. Not because the robots are poorly designed, because the question is genuinely hard. Detecting evidence of ancient Martian life, if it exists, may require the kind of subtle contextual judgment that is extremely difficult to encode in an autonomous system. When geologist Jack Mustard was reviewing Mars images and noticed that a particular rock exposure looked like something he had seen before in ancient shallow marine sedimentary sequences on Earth, that recognition was not a simple pattern match. It was a synthesis of decades of field experience, contextual awareness of the surrounding terrain, and scientific intuition about what matters. The Apollo program offered a direct lesson in what happens when human beings with scientific expertise investigate planetary surfaces directly. The samples returned by the Apollo astronauts enabled discoveries that no robotic mission could have produced. Not because the scientists who flew to the moon were smarter than the scientists who designed the robotic missions, but because the combination of geological training, contextual presence, and physical flexibility allowed them to make choices in the field that changed what came home. The giant impact hypothesis, the now accepted understanding that the moon formed when a Mars-sized object struck the early Earth, emerged from analysis of Apollo samples that showed oxygen isotope signatures inconsistent with simple formation alongside Earth. The first Mars geologist to spend weeks traversing ancient lakebeds and river channels and volcanic terrains with a full laboratory at their disposal will have access to something that no orbital, spectrometer, or arm-mounted drill can provide: the ability to follow a feature as far as it needs to be followed, pick up a rock that looks slightly wrong, crack it open, look at the fresh surface, and decide in that moment whether it deserves more investigation. That decision, made in the field, by a human being who understands what they are looking at, is where the most important Mars science will happen. The generations of people who will eventually inhabit Mars permanently are not yet born. Some of them may already exist. The children alive today who will train for Mars missions in the 2040s and 2050s are already in schools, already being shaped by the culture and knowledge and ambition of this particular moment in human history. What they inherit from this moment is not just a technology, it is a precedent. The first people to reach Mars will establish what a Mars mission is. They will define what it means to live and work on another planet by actually doing it. Every mission that follows will be calibrated against what they accomplished and what they failed to accomplish. The pressure on those first crews will be unlike anything faced by any space crew in history. Not the pressure of a 6-hour lunar EVA. Not the pressure of 6 months on the ISS before returning to Earth. The pressure of a commitment, measured in years, on a world from which no emergency evacuation is possible. The pressure of knowing that everything they learn and build and demonstrate will determine whether the program continues, whether the missions keep coming, whether the settlement grows or stagnates. The pressure of being, inescapably, the beginning. Beginnings are hard to live inside. The significance of a beginning only becomes clear in retrospect, when there is enough subsequent history to measure it against. The first Mars crew will not be able to see that retrospect. They will be too close to it. They will experience it as days and equipment failures and dust storms and meals from pouches and conversations with Earth that take 20 minutes to arrive and the particular quality of light through the habitat windows on a Martian afternoon. They will experience it as work, ordinary work, day after day, in an extraordinary place. That is how history is made by the people who make it. Not as the grand arc it becomes in retrospect, as the next thing that needs doing. There is something else worth saying about the footprints they will leave. The Martian surface is geologically quiescent by terrestrial standards. There is no tectonic activity to speak of. There is no liquid water to erode and redeposit material. There is wind, but the Martian wind, despite its speed, carries so little force in the thin air that it moves only the finest dust particles under most conditions. The footprints left by the first human beings on Mars will still be there in 10,000 years. In 1 million years, quite possibly in 1 billion years. The rocks that the first Mars crews pick up and examine, the tracks of their vehicles, the disturbed soil around their landing sites, the debris field of their descent hardware, all of it will persist on the Martian surface for geological timescales, because there is almost nothing there to destroy it. The Apollo landing sites on the Moon, similarly inert, will preserve their footprints for hundreds of millions of years. On Mars, the conditions for preservation are different in detail but similarly extreme. The first human footprint on Mars may be legible to future visitors for longer than multicellular life has existed on Earth. That footprint will be left by a specific person, a real human being with a name and a history and a reason for being there. That person exists somewhere right now, living a life that has not yet taken the shape of what they will become. They are being trained by something they do not yet know they are being trained for. And when they step out of an airlock onto the surface of another world, when the footprint is made, in the cold and the silence, under a sky that no human being has ever before breathed under or looked up at or called their own, the long argument about whether the first Mars mission would be a one-way trip will cease to matter. What will matter is that it happened. What will matter is that someone chose to go. What will matter is the footprint. But before any of this becomes history, rather than aspiration, there is a reckoning that the engineering has to win. The reckoning is with physics. Specifically, with a relationship discovered in 1903 by a Russian schoolteacher named Konstantin Tsiolkovsky, who worked out the mathematics of rocket propulsion and produced an equation that has governed spaceflight ever since. The Tsiolkovsky rocket equation relates three quantities: the velocity change a rocket can achieve, the effective exhaust velocity of its propulsion system, and the ratio of its initial mass propellant included to its final mass after the propellant is burned. The equation has an exponential structure. This sounds like a technical detail. It is the central fact of spaceflight economics. Exponential relationships behave very differently from linear ones. If you need twice as much velocity change, you do not need twice as much propellant. You need exponentially more. If you need to make a landing on Mars, launch off the surface, and then make the journey back to Earth, you are stacking velocity requirements on top of velocity requirements, and the propellant mass required grows at a rate that quickly becomes the dominant constraint on everything else you want to do. To reach low Earth orbit from the ground, a rocket needs to achieve roughly 9.4 kilometers per second of velocity. To inject into a trajectory toward Mars from Earth orbit requires roughly 3.6 kilometers per second more. To enter Mars orbit from the interplanetary trajectory requires a deceleration burn of about 2 kilometers per second. To descend to the Martian surface requires more deceleration. Mars has enough atmosphere to allow aerodynamic braking, but the atmosphere is thin enough that a significant propulsive burn is typically still required near the surface. So far, so demanding, but then you add the return. To launch off the surface of Mars requires achieving enough velocity to reach Mars escape velocity, or, more precisely, to enter orbit or a trajectory that will eventually intersect with Earth's orbit. The Martian surface escape velocity is about 5 kilometers per second. A minimum energy trajectory from Mars to Earth requires an additional burn at the departure point. Then, arriving at Earth, some form of deceleration to enter orbit or perform a direct re-entry. Earth's atmosphere can absorb some of this, but the approach velocity from Mars is high enough that thermal management during re-entry is a significant engineering challenge. Add all of this up across the full mission. The propellant required to bring a return vehicle to the Martian surface, fueled and ready for the return journey, is a substantial multiple of the mass of everything else in the mission. This is the tyranny of the rocket equation. It does not bend for ambition. It does not negotiate. It applies to every mission architecture equally. And it means that planning a full round-trip Mars mission with propellant brought from Earth requires launching an enormous quantity of mass from Earth's surface, so much that it fundamentally constrains what else the mission can carry. The most credible approach to solving this problem is called in situ resource utilization. The idea is to not bring the return propellant from Earth. Instead, manufacture it on Mars using materials available on the surface. The Martian atmosphere is 95% carbon dioxide. The Martian subsurface contains water ice at accessible depths in multiple locations confirmed by orbital radar. Carbon dioxide and water can be combined through a chemical process called the Sabatier reaction to produce methane and oxygen. And methane and liquid oxygen is a high-performance rocket propellant combination, the same combination used by SpaceX's Raptor engines on the Starship vehicle. The chemistry is well understood. The process works in laboratory conditions. The Mars Oxygen In Situ Resource Utilization Experiment (MOXIE) flew on the Perseverance rover and demonstrated that oxygen could be produced from Martian carbon dioxide using solid oxide electrolysis. MOXIE produced up to 10 grams of oxygen per hour during its demonstration runs. The amount of oxygen needed to launch a Mars ascent vehicle for a crew return is in the range of 25 metric tons. The gap between 10 grams per hour and 25 metric tons is not trivial. Scaling from a demonstration to an operational propellant production plant requires engineering at a level that has not been achieved anywhere on Mars. It requires power at a level that a solar-only architecture might struggle to provide during dust storm conditions. It requires mechanical systems, compressors, reactors, liquefaction equipment that must operate continuously and reliably in the Martian environment for the year or more required to accumulate enough propellant before a crew ever departs Earth. This is not an argument that it cannot be done. It is an argument for why mission planners who describe a conventional round trip to Mars as if it were simply a scaled-up Apollo mission are substantially understating the technical challenge. The surface propellant production approach can work, but it needs to work perfectly, autonomously, for a year or more, without human intervention, on a world where no human being has ever operated machinery, before anyone stakes their life on the assumption that the return tank is full. The honest version of the Mars mission planning conversation acknowledges that the first crewed Mars missions will almost certainly fly before that confidence has been fully established. The question is, what you do with that acknowledgement. You can pretend the risk does not exist and continue planning as if the propellant will be ready when the crew arrives. You can delay the mission indefinitely, waiting for a standard of confidence that the operational environment on Mars may never allow. Or you can redesign the mission around the reality of the situation, sending people who understand that the return capability is uncertain, who are prepared to stay if the return is not viable, who bring with them the materials and skills to build a sustainable presence rather than an extended camping trip waiting for a ride home. That third option is not defeatism. It is honest engineering applied to a problem that honest engineering shows is genuinely hard. The radiation environment of interplanetary space is a separate constraint that the mission planner who wants a conventional round trip must also confront honestly. On the surface of Earth, the planet's magnetic field and atmosphere provide substantial protection against the two primary sources of space radiation: solar energetic particle events, which are intense bursts of radiation associated with solar flares and coronal mass ejections, and galactic cosmic rays, which are high-energy particles accelerated by supernova remnants and other energetic astrophysical events throughout the galaxy. On the surface of Mars, the magnetic field is negligible. Mars lost its global magnetic field billions of years ago. The atmosphere provides some shielding, but far less than Earth's. On the surface of Mars, a person receives roughly twice the annual radiation dose they would receive on the International Space Station, which is itself many times the dose received on Earth's surface. During the transit from Earth to Mars and back, in deep interplanetary space, with no planetary atmosphere or magnetic field at all, the radiation dose is higher still. The estimates for a complete round-trip Mars mission, 2 transit phases, plus time on the surface, place the total radiation dose in the range of 800 to 1200 millisieverts over the course of the full mission. The current career radiation exposure limit for NASA astronauts is set based on a 3% increase in lifetime fatal cancer risk, and the specific number varies by age and sex at the time of exposure. But for most middle-aged adults, it is in the range of 600 to 1200 millisieverts. A full round-trip Mars mission pushes against or exceeds most astronauts' career limits in a single mission. Galactic cosmic rays present an additional concern that goes beyond the simple dose calculation. These particles are so energetic that conventional shielding materials are not effective against them. In fact, high-density shielding materials can make the situation worse by producing a cascade of secondary particles when struck by galactic cosmic rays. The best practical shielding for galactic cosmic rays in deep space may be water or polyethylene hydrogen-rich materials surrounding the crew habitat. But carrying enough of these materials to provide meaningful shielding adds mass, and mass, as the rocket equation makes clear, is the most expensive thing in spaceflight. One-way missions change the radiation calculus in a specific and important way. The transit phases, the months spent in deep space between the planets, are the highest radiation portions of the mission. A one-way mission eliminates one of those transit phases. A crew that goes to Mars and stays does not face the radiation dose of the return journey. Over the full trajectory of their lives on Mars, the surface radiation dose accumulates steadily. But the peak exposure events, the deep space transits, occur only once, not twice. For missions designed around extended surface stays, the one-way model actually represents a more favorable radiation budget than a round-trip model for the same surface duration. This is not a widely appreciated point. It sits beneath the surface of the public debate about one-way missions, which tends to focus on the psychological and ethical dimensions, while the physics quietly argue for exactly the approach that the ethical critics are questioning. The human body in microgravity deteriorates in ways that 50 years of spaceflight research has documented in detail and still not fully solved. The cardiovascular system, no longer working against gravity, redistributes blood toward the head and upper body. The heart, accustomed to pumping blood upward against gravity, begins to atrophy because the demand on it changes. Bone mineral density decreases at roughly 1 to 2% per month in microgravity because bone maintains its density in response to mechanical loading. And in microgravity, there is almost no mechanical loading from simply existing. Muscle mass decreases. Vision, in a significant fraction of long-duration space travelers, is affected by changes in intracranial pressure. The syndrome is called spaceflight-associated neuroocular syndrome, and it has produced measurable and in some cases persistent changes in the vision of astronauts who completed 6-month ISS tours. The immune system changes in ways that are still being characterized. The gut microbiome changes. The regulatory systems that manage body fluid distribution, bone turnover, and muscle maintenance are all calibrated to a gravitational environment they evolved in over hundreds of millions of years. Remove the gravity and they recalibrate to a new environment, and the recalibration produces changes that are harmful. The transit to Mars is 6 to 9 months of microgravity. 6 to 9 months of bone density loss, cardiovascular deconditioning, and elevated radiation exposure before the crew even arrives. A crew that has spent 8 months in transit and then needs to land on Mars, an event that requires manual control, fast decision-making, and physical performance under the stress of a complex entry, descent, and landing sequence, will be arriving with bodies that have been systematically weakened by the journey. Mars' gravity is 38% of Earth's. Nobody knows what 38% gravity does to the human body over years. We have good data on zero gravity and good data on full Earth gravity. We have no data on a fraction that falls between them. Whether 38% gravity is enough to prevent the bone loss, muscle loss, and cardiovascular changes that microgravity produces is genuinely unknown. Some researchers believe that even partial gravity would be substantially protective. Others are less confident. The data does not yet exist to resolve the question. The first Mars crews will generate that data. Their bodies will be the instruments of the first long-duration partial gravity experiment in human history. Whatever they find about their bone density, their cardiovascular function, their vision, their immune function after years at 38% gravity will be essential data for every Mars mission that follows. This is another dimension of the scientific value of a permanent presence that the pure engineering discussion tends to underweight. The mission is not just about Mars geology and the search for past life. It is also, inescapably, a study of what it means to be a human body somewhere other than the place human bodies evolved to inhabit. The findings will inform medical practice for every future interplanetary mission. They will inform the design of habitats and exercise protocols and nutritional strategies and medical interventions. They will tell us things about the human body that we cannot learn any other way. That is not reckless. That is how medicine has always advanced. Through the systematic study of people in conditions that differ from the baseline, carried out with their informed consent, in service of knowledge that benefits people who come after. The first Mars crew will be, among other things, a medical research team studying themselves. That is not a burden imposed on them. It is part of the reason they are there. There is a reason that every ambitious thing our species has ever done was done by people who had to be alive to do it. The risks were never the argument against going. The risks were part of the cost of the thing that needed to be done. And the thing that needs to be done, if our species is to have a future that is not confined to this one fragile world, is to learn how to live beyond it. That learning begins with a mission. That mission begins with a choice. That choice, if the engineering and the history and the simple trajectory of human ambition are any guide, will almost certainly be made by people who go, knowing they might not come back. Not because they are fatalists, because they understand that some things are worth the risk. And Mars, the ancient, frozen, beautiful, hostile, still mysterious Mars, that is closer to us in space than any other world we could plausibly reach, is the first one. The institutional history of Mars mission planning is, if you follow it carefully, a study in the gap between stated ambition and realized commitment. The gap is instructive. In 1989, NASA presented President George H.W. Bush with a proposal called the Space Exploration Initiative, a program to return humans to the Moon and then proceed to Mars. With a projected cost of approximately $500 billion over 30 years. Congress declined to fund it. The proposal was shelved. In 2004, the Vision for Space Exploration announced a return to the Moon by 2020 as the first step toward eventual human Mars missions. The Constellation program was developed to implement this vision. It was canceled in 2010. In 2017, a new architecture emerged under a different name and a different set of political priorities. The Moon remained the near-term destination. Mars remained the stated long-term goal. The pattern across these decades is consistent. Genuine technical progress, genuine scientific investment, genuine institutional desire to reach Mars at some future date, combined with consistent inability to maintain the funding, commitment, and political will required to actually execute in the time frame announced. This is not a story of incompetence. It is a story about what it costs to do something genuinely hard, and about the difficulty of sustaining political will across election cycles and budget negotiations for a program that pays its most dramatic dividends decades in the future. The entry of private spaceflight companies into this landscape changed something important, not the physics, not the fundamental requirements of a Mars mission, but the institutional architecture in which Mars missions could be planned and funded. A private company does not have to survive congressional appropriations hearings. Its founding vision can sustain investment across time horizons that would destroy any government program's budget justification. Its failures are expensive and public, but do not trigger the kind of political recrimination that grounds government programs. And its success, when it comes, is measured in demonstrated capability rather than projected schedules. The development of fully reusable heavy-lift rockets hardware that can be launched, recovered, refueled, and launched again, rather than being expended on each mission, changes the economics of Mars exploration in ways that the government program paradigm never could. When the cost of reaching low Earth orbit falls by an order of magnitude, everything built on top of that foundation becomes more accessible. The propellant depots that make deep space missions practical become affordable. The pre-positioned cargo missions that establish supply caches on Mars before any crew departs become feasible within a planning horizon that institutions can actually commit to. The redundancy of multiple vehicles per mission, because each vehicle costs a fraction of what it previously did, becomes standard practice rather than a luxury. None of this happens on a schedule anyone can reliably predict. Rocket development is hard. Reusability is hard. Achieving the cost targets that make the economic argument work is hard. But the trajectory is visible. The hardware is flying. The lessons from each mission are being incorporated into the next design cycle faster than any government program has historically managed. The Mars that the first human crew will reach is already being prepared for their arrival by the robotic missions running ahead of them. Perseverance is caching samples from an ancient lakebed that may represent the best chance humanity has ever had to find evidence of past Martian life. The Ingenuity helicopter demonstrated powered flight in the Martian atmosphere, opening an entirely new mode of surface exploration. Future missions will attempt to return the Perseverance samples to Earth, a mission of extraordinary complexity that will serve as a test case for many of the rendezvous and proximity operations that a crewed Mars mission will require. The ground is being prepared, the knowledge is accumulating, the hardware is being developed. The people who will fly are training for it, or training for things that will train them for it, or being born. The question of whether the first Mars mission will be one way is not ultimately a question that will be answered by argument. It will be answered by the mission that actually happens, by the crew that actually goes, carrying whatever combination of return, capability, and permanence the mission architecture they depart under has provided for. But the argument matters because it shapes the mission. The way you think about return changes, what you build, what you bring, what you train for, what you commit to in the design of the habitat and the power system and the food production capability. A mission designed around the assumption that everyone comes home in 2.5 years carries different infrastructure than a mission designed around the assumption that some, or all of the crew stays. The difference is not small. It is the difference between an expedition and a settlement, and the history of human expansion suggests that the most durable and significant human expansions were not expeditions, they were settlements. The people who are alive right now, reading about Mars missions and watching rocket launches, and perhaps working in the fields that will eventually make the mission happen. They are part of the generation that will decide which kind of mission this is. That is not a small thing. There is a silence that settles in when you follow all of this to its honest conclusion. Not the silence of running out of things to say. The silence of having reached the edge of what is certain and arrived at what is genuinely open. The first Mars mission will almost certainly not be a conventional round trip in the sense that Apollo was. That is, the honest conclusion of the engineering analysis. The mass requirements, the technology readiness of in situ propellant production, the physiological demands on the crew of a full return transit following years on the Martian surface, the complexity of the ascent vehicle systems needing to function perfectly after years of autonomous operation. All of it points toward a mission model in which either the return capability is pre-positioned and demonstrated with extraordinary reliability before any crew departs, pushing a truly conventional round-trip mission well into the future, or the first crew goes with the intention of staying, with return made possible only by the infrastructure they help build once they arrive. The choice between those two paths is not purely a technical decision. It is a question about what a civilization is willing to ask of some of its members for the benefit of all of them. It is a question about what kind of mission this is, an expedition or a settlement. The history of the species suggests that the most enduring human expansions were not expeditions, they were settlements. The people who changed the distribution of our species across this planet were not the ones who went and came back with reports. They were the ones who went and stayed and built things that lasted after them. The technology for the next expansion is being built right now. In facilities and launch sites and design offices, the hardware that will eventually carry human beings to Mars is being assembled, tested, broken, and rebuilt. The people willing to go are alive right now. The institutional commitment, however inconsistently funded and however often restructured, has not reversed. The direction of travel is set. Mars will be reached. The question is when. The question is who will be on that first vehicle. And the question, honest and open and not yet answered, is whether the door closes behind them with a return ticket in someone's hand, or whether the first footprints on Mars are left by people who understood, before they boarded, that they were not building a mission. They were building a home. That is not recklessness. It is not tragedy. It is the oldest impulse our species has ever acted on, the impulse to go anyway, to build anyway, to reach towards something you cannot be certain of returning from, because the alternative is to look at the universe from this one small world forever. And that is not the kind of species we are. Subscribe for more journeys into the cosmos, and remember, somewhere out there, beneath a sky, the color of butterscotch and rust, the next chapter of the human story is waiting to be written, not by a machine, by someone who left everything behind and arrived.